Hi there. First and foremost, a very big thank you to the Strength and Conditioning Society for inviting me to be a part of this very exciting new course. The content of this presentation will be addressing physical performance assessments in football or soccer, with a focus on providing information around the various different field and laboratory-based testing methods for the physical capacities that are important for the sports. Now, before embarking on going straight into the tests that we need for football, I think we should take one very small step back and first consider how is it that we know certain tests or physical capacities need to be assessed in the sport? And of course, the answer to that is we would undertake a needs analysis for football, and we might do that for the sport in general, but we also might do that on a more position specific basis as well. This presentation will just cover a generic needs analysis for football, and as a consequence of that, we'll start talking about essentially 7 key areas that are probably really important to assess for the sport. And that's strength, power, linear speed, change of direction speed, aerobic capacity, repeated sprintability, and anthropometry. And then in order to try and inform all the different tests and how usable they are in practice, both from a pragmatic perspective and from a more robust statistical perspective, we'll provide some information on previous research, the reliability of these different tests, and their associative links with performance or injury risk. And then essentially what we've concluded at the end of the presentation is some information around perhaps an optimal testing battery for the sport, but also a sort of plan B if you work in the field with limited resources, limited budget, and you have a finite amount of time to work with a large group of players. Okay, so before embarking on any information around the needs analysis of the sport or any specific testing methods we might consider, I wanted to provide some operational definitions for everyone because they're going to keep coming up throughout the remainder of the presentation. And they essentially are based around either reliability, correlations, or effect sizes. So first and foremost, reliability is really important because initially it provides a filter check that the data is consistent and usable, and therefore we're able to undertake further analysis, whether that be correlations or we're trying to assess differences or levels of agreement, whatever it might be. But the other reason as well is that measures of reliability represent the noise or the natural variability in a squad or an athlete's testing scores, and that represents the marker or the threshold that we need to exceed next time that we test to establish true or meaningful change. So it's not just, oh, my data's reliable and I can use it. It's also that the reliability score is the value that we need to use to establish the sensitivity to change of a test. From a correlation perspective, the other reason we're going to be talking about relationships or associative analysis or correlations throughout this presentation is because once you know that a test is reliable, the reason you would choose a test is because there is a biological basis for using it. And the biological basis is determined by making sure that your test or your outcome measure is related back to some other measure of performance that's associated in the sport. And then lastly, from an effect size perspective, some of the studies I'll be discussing will be focusing on differences because they've run an intervention. And essentially the effect size gives us an understanding of practical differences or practical magnitude of change. So specifically, if we talk about those 4 boxes at the top, the coefficient of variation is a measure of absolute reliability, And essentially we're just trying to understand how consistent the data is between trials or test sessions. So it gives us a measure of the natural variability that that athlete exhibits or that test shows either within or between session. Now, various different scales exist, but I think that one that Harry Banyard has suggested is really, really nice. The intra-class correlation coefficient is a measure of relative reliability, and it's essentially a measure of rank order consistency, i.e., how consistently do your athletes appear within the same position or ranking for a given test or set of test scores. From a correlation perspective, we would use Pearson's R correlation for normally distributed data, or we would use Spearman's rank order correlation for non-normally distributed data. And you can see the scale of interpretation provided by Will Hopkins there. I think it's important to point out as well that practically speaking, we're probably only interested in any correlations that are greater than 0.5 or minus 0.5, depending on the direction of that correlation. And then lastly, to discuss effect sizes, I think it's advantageous to have an understanding of what effect sizes mean, because historically we rely on null hypothesis statistical testing in sports science, whereby we are trying to determine whether an intervention is meaningful or significant. And the way we do that is by using a p-value of 0.05. And essentially what that says is that we're more than 95% sure that the observed effect or change is greater than any measurement error or random sampling frequency errors in our study design, and it's entirely down to the intervention that we've conducted. However, in sport, we probably embrace the grey areas a bit more than that, don't we? Whereby if I went to a manager and I said, look, I'm not 95% sure this is going to work, but I'm about 90% sure, or I'm about 85% sure, the manager would probably turn around and say, okay, give it a go. So effect sizes give us an understanding of practical differences rather than statistical differences. And this scale proposed by Hopkins, again, is probably one of the most commonly used when we can't guarantee that every study that we're going to be talking about has the same level of athlete in it. Okay, so they're not all elite and professional players. Some are youth, some are academy. And so taking a somewhat more generic approach to using effect sizes is probably sensible here. Okay, so when we now start looking at the needs analysis of football, and naturally there's a lot of literature out there on this sport, a good place to start is usually narrative review articles or systematic review articles or meta-analyses, because they tend to encompass a whole range of literature, studies and information into one area. And there's a couple of very nice narrative review articles in the NSCA's Strength and Conditioning Journal by my colleague Anthony Turner, as you can see here. And he's kind of looked at the different strength and conditioning requirements for soccer players and a proposed fitness testing battery. And when you look at this type of summary information, what we typically get is 7 kind of physical capacities or qualities that typically come out of the literature that practitioners probably need to consider assessing. And they are body composition, strength, power, linear speed or sprinting ability, change of direction speed ability, repeat sprint ability, which is a very important one in football, and of course aerobic capacity. So the rest of this presentation is now going to go through each of those 7 different components, offering information on the different laboratory and field-based tests that we can use, their usability and their kind of general association with other independent measures of physical performance for the sport of football. You should also probably note that particularly when we get to things like linear speed and change of direction speed and repeated sprintability. Yes, you can assess those physical capacities in the laboratory, but I've only really focused on tests and protocols that are conducted in the field. So we'll start by looking at body composition or anthropometry first, and specifically in the laboratory. And there's probably about 4 methods that we can utilize in the lab for this, and I've only put 3 pictures up, and that's because something called hydrostatic weighing in water I just don't really feel is used much at all, or if ever now, particularly in sport. But bioelectrical impedance analysis, BIA, is one where you can either hold a device that will essentially read your body fat percentage through the use of electrical currents, but you can also use BIA through having electrodes attached to your skin, which again sends an electrical current through your body. Below that is a DEXA, which is probably, or not probably, actually almost certainly considered the gold standard method of assessing body composition. And you can see that gentleman lying down on what looks to be a bed, and part of the device that is over his face is, I guess, best described as a movable arm that travels very slowly all the way down his body, which probably takes somewhere between 6 to 8 minutes to complete. And then on the right we have something called a bod pod, which people can sit in. So essentially we're just going to talk primarily about these 3 methods, and only very, very briefly, because as accurate as these laboratory-based methods are, particularly the DEXA and the bod pod, the money required to purchase this piece of equipment is extremely high, and they're usually only accessible in high-profile private laboratories or universities. So I'm just not sure that the accessibility of this type of equipment for practitioners or athletes working or playing in the sport of football, it's just not particularly viable. But worth noting, particularly from the DEXA perspective, because it is a gold standard method for assessing body composition. So this is the first study we're going to look at, which essentially just looks at the reliability, or the between session reliability, of the DEXA scanner using 2 different types of methods or settings on the DEXA. One is called the fan beam and one is called the pencil beam. Now, the pencil beam is the original method of using a DEXA scanner, and essentially just provides one single X-ray beam to scan the entire measurement area, or measurement area in this case, of course, being a human body. The fan beam, however, uses multiple detection points for the X-ray. So essentially it has multiple X-ray beams scanning the measurement area. Now the thought process is that when you use multiple X-ray beams, it might provide a slightly larger margin of error, because, you know, where one beam ends and where one beam starts has to be absolutely perfect in order to avoid overlap or a very minute part of the body being missed. But actually, if we look at the reliability data, you can see here that generally speaking, the reliability of the fan beam tends to be better. Remembering that our scale is less than 5% for CV is good, and every single CV value for the fan beam is under 5%, whereas for the pencil beam, that second set of data, we've got a number of different areas that are still showing moderate reliability, i.e. CVs between 5 and 10%, but the fan beam does appear to be slightly better. And then I think the ICC values are essentially much of a muchness. They're almost all of them nearly perfect, and as a consequence, it probably doesn't really matter that much whether you use a fan beam or a pencil beam, remembering that the DEXA in general is just without question, the gold standard method of assessing body composition. If we move on to the bod pod now, I actually struggled to find retest reliability of a bod pod that wasn't part of some kind of training intervention. Now, I know this is a sports science presentation and module, and it's not specific to nutrition, but if we focus on our coefficient of variation values for our different metrics, which is body fat percentage, fat-free mass, body volume, and body fat via the 7-site skin fold method, well, actually we can see that our coefficient of variations are all less than 10%. So as a minimum requirement, everything we see, with the exception of the skin fold method, is moderate or good reliability, which is useful. I also think it's worth noting, though, that they've reported the coefficient of variation as a consequence of looking at the difference between pre and post. Now, the issue here is that when you run a training intervention, you are trying to induce change in someone's anthropometry or test scores. And the bigger the change, the worse the reliability will be, because the CV is looking at measures of consistency. So I wasn't able to find retest reliability for the bod pod. The only one I could find was this, which is following a training intervention. So I think it's worth noting that although we see values of 7.12 and 7.26 and 8.92 for the coefficient of variation, it's after a training intervention has been conducted where they are trying to induce change in body fat percentage and fat mass percentage. So we need to be a little bit mindful, and actually these CV values might not be completely indicative or accurate of the actual reliability of the bod pod system. But having said that, it was all I could find, and it does seem that even after a short nutritional intervention, that as a bare minimum, results are either good or moderate. And so probably if you do have access to a laboratory, then, you do have access to a laboratory, but you don't have access to a DEXA, the bod pod certainly represents a good plan B or second option. So we'll move on to body composition methods that are typically conducted in the field, and there's probably only really one method to focus on here, and that is skin fold assessments through the use of calipers. And there's a number of different methods and equations used to predict overall body fat percentage using calipers, and that will depend on how many sites are tested. You can see that figure on the right provides an example of different places within the body to assess, and essentially provides about 8 different locations on the body. And there are other formulas and other methods that utilize 6 and 4 sites on the body. But I think the primary message should be it's heavily driven by experience and skill, the accuracy of the data when using calipers. And there's an organization called ISAC, which is the International Society for the Advancement of Kinanthropometry, and they offer different level certifications for conducting this type of testing. And I'd probably suggest that no one undertakes this without having either been taught by someone who's very experienced in the field or has an ISAC certification as well. So this infographic represents a really nice summary of a study conducted in 2018, whereby the authors were trying to determine the level of accuracy and the relationship between different skin fold assessment methods or equations with the DEXA scanner, which of course would be our gold standard method. So you can see that on the bottom we've got this kind of color-coded correlational scale, where the further right you are, where it's green, we've got strong relationships between skin-fold equations and what the DEXA produces for predicting percentage of fat mass. And then also the vertical axis aims to determine how much mean bias each of these methods or equation offers, again, relative to the DEXA. So anything above 0 would suggest that these equations overestimate the percentage of fat mass, and anything below 0 underestimates. And then the further right you go, the stronger the relationship. So you can see that, generally speaking, none of these equations overestimate or underestimate percentage fat mass by more than about 2%. However, there is a distinct difference between some of these equations and how strongly they're associated with the DEXA. So you can see that Durenberg actually only has a relationship of around about 0.34, 0.35, whereas Faulkner and Durnin and Wormsley, actually their relationship is around about 0.8, or just over or just under. So this should give us an understanding that the general mean bias is acceptable. It tends to be less than around about 2%, but actually some of them are much more strongly correlated with the results you get from a DEXA scanner. And so we should probably be selecting the formulas or the equations that are furthest to the right in green. And then as a final summary for whether or not we should be considering using skin fold assessments, this is a fantastic infographic by my friend Adam Virgil, who typically creates these on behalf of the National Strength and Conditioning Association. And I won't read everything that's on here, but what is interesting to point out is that in a survey conducted, typically the ISAC or other skin fold methods were far more popular than methods like the DEXA scanner, BIA, or hydrostatic weighing. And that's of course because they're far more accessible to practitioners in the field, given that the other types typically require very, very expensive equipment and are of course confined to a laboratory. They've also got a number of pros and cons for using skin fold assessment, which is a really nice summary so that practitioners can consider whether or not the advantages outweigh the disadvantages for using this sort of method. But actually, for those practitioners that are essentially governed by not having a very large budget, then there is of course a trade-off in terms of accepting that there will not be as accurate data using this method, but perhaps if we choose an equation that's quite strongly correlated to the results from a DEXA scanner, and we learn to improve our skill at collecting skin fold assessment methods over time, we should expect the data to become more reliable as we become more accustomed to the test methods. And perhaps using skin fold assessment is better than doing nothing at all, particularly for athletes where excess body mass or body fat might impair performance by reducing their ability to sprint, jump, or cover greater distances on the pitch. Okay, so now we'll move on to looking at the importance of strength, and we'll start in the laboratory for this. Now, there are probably a number of methods to assess strength that in reality could be conducted in both the laboratory or the field, but I've tried to confine this laboratory-based strength section purely to isokinetic dynamometry, because this is a method that is strictly used in the laboratory only, and all the other methods that could take place in a laboratory, such as isometric mid-thigh pull testing, isometric testing for the hamstring, using a Nord board, they come under assessment methods for the field, knowing that they are also commonly utilized by practitioners and they're not exclusively confined to the lab. Now, one of the most common uses of isokinetic dynamometry is to report hamstring quadricep ratios. And this is a fantastic study by Franco and Pellizzeri, who I'm sure many of you will have heard of before. And essentially what they looked at was concentric and eccentric measures of hamstring and quadricep peak torque. But this particular table is looking at the reliability through the intraclass correlation coefficient and the standard error of measurement for hamstring to quadricep ratios on each limb, right and left, and then also looking at bilateral quadricep and hamstring ratios, so effectively looking at interlimb asymmetry at different speeds. You can see there that we've got concentric peak torque contractions at 60, 120 and 180 degrees per second, and then the bottom row under each of those ratios is eccentric to concentric for the top two, and then eccentric at 60 degrees per second. Now, the reason why this study was so good is because we're reporting between session reliability rather than intra-session reliability. Between session reliability studies are often conducted over 2 sessions, but Franco and the team actually did this over 3 test sessions, which was excellent. And I guess the main thing to point out here is that we're not measuring raw peak torque values. We're measuring the reliability of the ratio itself. So once we've got our peak torque values for the hamstrings and the quadriceps, that is then used to create our ratio statistic, our H to Q ratio number here at all these different contraction speeds on the right leg, on the left leg, and then an interlimb ratio for the quadriceps and the hamstrings, again at different speeds. Now, when we look at our ICC values, remembering that at the beginning of the presentation, or at the beginning of this series of slides, what we went through was anything greater than 0.9 would probably be considered excellent reliability or an excellent ICC. Anything above 0.75 would be considered good, but anything less than 0.75 is either moderate and then less than 0.5 being poor. So if we now start scanning this column of data labeled ICC, you can see there's 2 things to note. Number one is that actually a lot of these ratios are displaying either moderate or poor reliability. You can see there's 0.34, 0.55, 0.44, 0.43, 0.29. So actually a lot of these ratios exhibit quite poor reliability, which is something that is important because we shouldn't be prioritizing the use of data that is inconsistent or unreliable. The second thing to note is that whilst it's not a perfect linear trend, as the speed of contraction increases, typically the data becomes less reliable. So at 60 degrees per second, which is quite force orientated and at a relatively slow speed, you can see we've got ICC values of 0.79, which is good, 0.65 moderate, 0.78, which is good, and 0.59, which is moderate. However, once we start getting up to 180 degrees per second, 0.34 is poor, 0.44 is poor, 0.43 is poor, and 0.54 is barely moderate. So I think it's important to understand that there is a tendency when using isokinetic dynamometry at faster contraction velocities for the data to be a little bit less reliable. We haven't seen that a lot in the literature, and I think that's not only something that this particular single paper shows, but years of experience of us testing different athletes in our laboratory at the London Sport Institute at Middlesex has also shown us the same thing. And I think that's a really important factor for practitioners to be mindful of. In contrast, though, if we look at the raw data, which is from the exact same study by Franco and his team, what we now see is instead of the reliability of ratio data, we are now just looking at the raw peak torque scores for the quadriceps and the hamstrings on the right leg and the quadriceps and the hamstrings on the left leg, again at these different contraction velocities. And whilst I didn't focus too much, excuse me, on the standard error of the measurement, you can see that these standard error of measurement percentages are typically lower than what we saw for the ratios, and also our intra-class correlation coefficient, our relative reliability values are all absolutely excellent. We haven't got a single value that's less than 0.9. I think the lowest one there is 0.93. So I think the key takeaway here is that actually the measurement of peak torque and during isokinetic dynamometry, it is probably very, very reliable. The problem in the data comes about when we start pooling data together from multiple sources to create ratios or indices. That's when the data becomes much less reliable. And when the data is much less reliable, it's of course harder to use it to inform decision making in practice. So I'm not sure and I'm not convinced how usable hamstring to quadricep ratios are, particularly when all the information from that ratio can be obtained just by looking at the raw data for hamstrings and quadriceps separately. Now, whilst I only outlined a single study looking at the reliability of raw data versus ratios from isokinetic dynamometry, a lot of the existing literature surrounding this type of assessment follows a similar pattern to what Franco's study did. But from a more holistic perspective, particularly for practitioners working in a sport like football, I think for this type of testing method, knowing that it's confined to a laboratory, we need to seriously consider what the advantages and the disadvantages are, and whether or not those advantages outweigh the disadvantages. And if so, that may inform actually whether or not we should be using it. So some of this is based off anecdotal experience, not just the research, and it just serves really as a summary schematic for you to start thinking about yourselves, and it's not a fully exhaustive list either. But from a pros or an advantages perspective, I think there are definite advantages to having isolated muscle testing, i.e. only focusing on the quadriceps or the hamstrings, particularly in a sport like football where hamstring injuries are unfortunately quite common. Having isolated muscle testing to determine their strength is definitely a good thing. And being able to do that at various contraction speeds is also very advantageous, because football is played with both high force and high velocity. So being able to have an understanding of the strength of a given muscle that is prone to injury across a whole force velocity spectrum is really, really advantageous. And its potential to perhaps inform return to play decision making for injured players is useful for sure. And then finally, I think we can even consider not testing isokinetically, but testing isometrically on this piece of equipment and having angle-specific assessments of isometric torque. And that could be very, very useful if we know that there are certain length-tension relationships within the quadriceps or the hamstrings where that particular muscle is predisposed to a greater risk of injury. However, on the opposing side, from a cons or disadvantage perspective, well, this method is of course confined to a laboratory and the equipment costs a lot of money. So the ability for practitioners to use this piece of equipment
is probably only determined by whether or not you work for an absolutely top-notch, high-level elite club like your Barcelonas, your Bayern Munichs, your Real Madrids, your Manchester Uniteds. And for the most part, clubs probably have to partner up with universities in order to be able to gain access. So that is quite restrictive, and of course that creates an awful lot of time for testing. So it's hard to do that and implement that with large squads of athletes. Perhaps it's only really feasible for players who are injured. And even then, if you don't have that equipment, you still have to forge that link with most likely an academic institution that does have one. We also need to consider the relevance of the test position, because as advantageous as it is to be able to assess isolated muscles at various contraction speeds, the testing is almost always done in a seated position, and the mechanism of hamstring injuries in football is very rarely done in a similar position. So we have to consider whether or not the relevance of the test position is a hindering factor here. And of course, because of that, that dampens the ecological validity of this testing protocol, knowing that there probably is a relatively poor link to performance because players are never seated, the injuries don't happen in that position. So whilst there are advantages and disadvantages for isokinetic dynamometry, practitioners need to really carefully consider whether the pros do outweigh the cons, especially when there are probably quite a number of viable methods to assess strength in the field. Now, they might not assess the exact same thing, but I think the number of alternatives in the field probably outweighs our necessity to use isokinetic dynamometry. But of course, you must make that decision yourselves, and we'll now go on to talk about some of the methods of assessment for strength in the field. So there's 3 different methods of assessing strength that I'd like to focus on, but there aren't only 3 methods of assessing strength. I just believe these are probably the most important for footballers. And the first of those is an isometric hamstring assessment on a force plate that I believe was developed by Alan McCall. The second method is, again, an assessment of hamstring strength, but through the use of the Nord board, which I'm sure many of you will be familiar with. And then the third is an assessment of maximal isometric force production using the isometric mid-thigh pull. So the first method we'll focus on is the isometric hamstring test, and this is a fantastic study by Alan McCall and colleagues. Now, what you see in the picture, first of all, is one foot placed at 90 degrees at the hip and the knee joint, and then the heel positioned on top of a box with a force plate positioned on top. Now, the goal of the test is to effectively push down as hard as you can into the force plate for the specified time period, usually 3 to 5 seconds. Now, what this doesn't show is that they also tested at a different position at 30 degrees at the knee joint. So effectively that would look like the leg being 60 degrees straighter, if that makes sense. So just a very small knee bend. And the reason that these 2 angles were chosen is because one of the angles is specific to the greatest level of activation that you can expect in the bicep femoris. And the 30 degrees was chosen, I'm recalling from the paper now, I think because this is typically the angle where we might see the greatest risk of injury occurring. So the top table, you can see that we've got coefficient of variation, typical error, and ICC intraclass correlation coefficients for peak force at 90 degrees and 30 degrees on both legs individually. And remember, if we go back to our acceptable reliability values, you can see that all CV values being less than 6.31%, tells us that, generally speaking, these values are relatively consistent, and the ICC, all being above 0.86, tells us that generally the relative reliability of peak force in this assessment is both good and excellent, okay, at both angles. Now, the other thing that they looked at was the sensitivity of this assessment to detect a drop in isometric hamstring force after a competitive match had been played, which again was quite clever, really. And what you can see is they've reported a percentage drop-off in force for each leg at each angle, what that is in raw values, and then presented that data, that difference between baseline as an effect size. And you can see that we're getting generally between an 11 and 16% drop-off in force, which represents a large effect size for each leg at each angle. So not only is this isometric test reliable, it's quite quick and easy to do, it's sensitive at being able to detect meaningful change in hamstring force or hamstring strength after a match, so serves as a really, really useful testing method, particularly in a muscle group which is so prone to injury in this sport.
If we move on to look at the Nordic hamstring exercise via the Nord board, this is a study that we actually conducted last season in professional football, where weekly Nord board testing was conducted throughout a 6-week off-season period, and we used the first 2 weeks for familiarization, and then we recorded data over sessions 3, 4, 5 and 6, so over 4 test sessions, and we gathered that data for dominant and non-dominant limb, and also looked at the interlimb asymmetry and peak force that we got from the Nordic hamstring exercise. Now, the first thing to tell you is when we start looking at the differences between test sessions, that was quantified through Hedges G, and we can see that generally speaking, differences tended to be either trivial or small, but we did get one moderate difference for between sessions 1 and 2 for the non-dominant limb, and you can see that just by looking at the raw scores in session 1 of 408 newtons versus 362 newtons in session 2, and we put that down to a slight increase in volume load that these professional players were experiencing between weeks 3 and 4 of the pre-season. If we also look at the reliability of peak force, which is that second table or table 3 at the bottom there, we've reported coefficient of variation percentage and intra-class correlation coefficients, but we've only reported between session reliability between consecutive test sessions. And as you see, we've got coefficient of variation that's ever so slightly elevated on the dominant limb between session 1 and session 2. Other than that, all CVs are less than 10%, which tells us that we've probably just about got acceptable consistency in our data between test sessions. And equally, generally speaking, ICC values are either moderate or good. We don't have one that's poor, but equally we don't have one that's excellent. And so there's probably a little bit of a learning effect in the Nordic hamstring exercise. Now, these were 14 professional players, so practitioners should just be mindful that in a muscle group like the hamstrings that tends to be a lot weaker than the quadricep, a muscle group that tends to have quite a lot of injuries within the sport, and also in an exercise that's quite frankly really quite difficult, the eccentric Nordic hamstring exercise, there is going to be a little bit of variability in the data, but generally speaking, the results showed us that assessment of peak force on the Nord board is acceptable. The other thing that I should mention, which I haven't included in this particular presentation, is there's a fantastic study by Nicole van Dijk, which I don't think was exclusively conducted in football players, but they did show that training programs that are inclusive of the Nordic hamstring exercise are able to reduce hamstring injuries by around about 50%. So not only is this a fantastic exercise for inducing eccentric strength in the hamstrings, which also helps to promote increased fascicle length in the muscle, but actually it's also a reliable test measure. And as a consequence of it being a reliable test measure and a good exercise, it seems like it's got effective, or it seems like it is effective, at helping to reduce non-contact hamstring injuries by virtue of improving both flexibility and strength concurrently. So if we stay with the Nordic hamstring exercise now, this is a separate study that looked at the relationship between this exercise and 20-meter sprint time in 119 youth footballers. Now, of course, it's important that there's a biological basis for any test that we choose to implement in our testing batteries. And what that means is that a test is strongly correlated with an independent measure of physical performance, or it can be used as a proxy that's sensitive to change to tell us something important. So in this instance, we can see from the graph that in these 119 youth football players, the higher the Nordic strength value, typically the faster these players ran. Now, the R-squared value is only 0.271, but that gives us a correlation of about 0.52. So generally speaking, that's bordering on sort of a moderate to large correlational value. So typically, it's more common than not that greater hamstring strength is associated with faster sprinting time. So this also gives us, excuse me, a reasonably strong justification for why we would also include the Nordic hamstring exercise as an assessment method, not only because the hamstrings are commonly injured in football, but also because hamstring strength appears to be a related factor for how fast these players can sprint. And of course, sprinting is one of the most common physical attributes that occurs during competition. Now, the third assessment of strength that I want to talk to you about is the isometric mid-thigh pull, and this is very much a test, or a multi-joint test of maximal force production capability. And this particular study was done in youth players, and you can see from table 1 there that there was 3 metrics of interest, which is looking at the absolute peak force value, relative peak force, and that is peak force relative to body mass, and the force that's produced at 100 milliseconds on the force time curve. Now, the reason that looking at force at different time points has become quite popular is because metrics like rate of force development have shown quite questionable reliability values, and so we're starting to see them being used less and less. Now, table 2 here shows an array of different reliability data for these 3 different metrics. We can see that we've got typical error, ICC, CV percentage, and minimal detectable change. And this is, of course, between session reliability done in the exact same way that we did for our Nordic hamstring exercise. So this was looking at session 1 versus session 2, then session 2 versus session 3, and session 3 versus session 4. And this is done in that chronological order to try and determine whether there's any learning effect for these metrics. So that whilst we can look at all of these reliability data, the 2 that I'd like to focus on the most would be the ICC and the CV value. And you can see that for absolute peak force, our CV tends to get less as the number of sessions goes on. We can see values of 8.1, 7.8, and then finally 5.8, showing us that generally the assessment of peak force starts to get more consistent as more test sessions are done. That's also represented by the ICC value improving from 0.69 to 0.88. There's a very similar trend in relative peak force, which would be expected because the force value only changes because of a division by body mass. But then it's important to outline that we start to see less consistency, i.e. higher coefficient of variation values for force at 100 milliseconds. And whilst values between sessions 3 and 4 at 8.8% are probably just about acceptable, values of 16.9 and 11.8% are probably too high and indicative of that metric being a little bit too noisy and unreliable. So I think the take-home message from this, given that it was done over 4 test sessions, is that looking at absolute and relative peak force data is almost certainly reliable and usable, but metrics such as force at 100 milliseconds, maybe there's a slightly larger learning effect for metrics like that, and particularly metrics like rate of force development, which weren't looked at in this particular study, but are often quite unreliable. So I think we can say with confidence, not just from this study, but from lots of studies using the isometric mid-thigh pull, that measures of peak force are definitely reliable and usable, as are relative peak force values if you wanted, excuse me, to compare across different age groups or genders. However, beyond measures of peak force, force at different time points, rate of force development, I'm not sure how usable those metrics are. And so it does beg the question that although we can conduct the isometric mid-thigh pull both in a laboratory and in the field, it is quite an extensive protocol to go through purely to get only one single metric of peak force that's usable. And then as a final slide for this strength section, I thought I'd present an array of different correlations looking at the relationship between isometric mid-thigh pull metrics and different athletic performance measures. And this was done in English professional soccer players. So for our strength measure, we've got absolute and relative peak force, and then we've also got force or relative peak force at 150 and 200 milliseconds on the force time curve. And those variables or metrics are being correlated against jump height during the counter movement jump, 10-meter sprint time, maximal sprint speed. So that measure is actually being measured in velocity, so meters per second rather than time, and then 5:05 sprint time. Now you can see we don't have relationships, we don't have meaningful relationships for all of these metrics, but we can see that peak force tends to be largely associated with how high you jump and how fast you sprint in terms of velocity. We've got correlations of 0.54 all the way up to 0.76. And actually relative peak force is also associated with peak velocity as well, with correlations of 0.51 and 0.66. And those correlations are positive, meaning the larger the force value, either the higher you jump or the greater the velocity measurement. Okay, so higher meters per second values. However, for 10 meter and 5:05, because the outcome measure is time, and the most desirable outcome for a time-based measurement is the smaller value, the correlations are in the opposite direction. We see negative values of 0.53, 0.55, and then for the 5:05 test, minus 0.6 to minus 0.68. And what that tells us when we look at the correlations between these mid-thigh pull variables and 10 meter or 5:05 times is that greater strength or greater relative strength is associated with faster 10-meter times and faster 505 times. And that is because for the strength test, the most desirable outcome is the larger value. But for the 10-meter and the 505 test, the desirable outcome is the smaller number because the outcome metric is time, not velocity. So if we have to sum this up, we can say that actually, although it is relatively extensive protocol undertaking the isometric mid-thigh pull, and there's probably a bit of a learning effect, particularly in youth players, there are some strong correlations with a wide variety of physical performance assessments that would be of great interest to football practitioners. You know, the counter movement jump is very commonly used and often used as a proxy for measurements of lower body power. We know that change of direction speed is incredibly important in football because of the sheer amount of changes of direction players go through. By virtue of change of direction, speed and agility being important, so too is acceleration, because acceleration forms a huge part of change of direction speed. And of course, peak speed or maximal velocity, MSS, is also incredibly important given the prevalence of sprinting during football. So actually, we've got quite a strong basis for including something like the isometric mid-thigh pull in our testing protocols because it's quite strongly correlated with a wide variety of physical performance assessments that are relevant for football players. What we'll do now is we'll move on to looking at the assessment of power, and rather than having separate laboratory and field subsections, we're just going to be talking about a variety of different jump tests that we can use as an indirect assessment of power, which we know is incredibly important for footballers and all team sport athletes, really. So given our focus is on jump assessments, whilst there's an array of different jump tests that we can use, we're going to center most of our discussion over the next sort of 8 to 10 slides in this talk around the squat jump, the drop jump, the counter movement jump, and the standing broad jump as well. So I thought the first thing I'd do is just provide a brief overview of the reliability of these different tests that we're going to talk about. And you can see I've provided a range in both the coefficient of variation and ICC values for squat jump, counter movement jump, drop jump, and standing broad jump. Now, the first thing to notice is that the slightly higher CV values and the slightly lower ICC values, particularly in the squat jump and the counter movement jump tests, are associated with children or youth athletes. So there's obviously a little bit of a learning effect when we're working with youth athletes, typically compared to adults, and that's something that we should be mindful of, ensuring that we give enough familiarization and our test instructions are incredibly clear. The other thing to say is that actually for the squat jump, counter movement jump, and drop jump, all of these reliability values are only for jump height, and that is because all of these references on the right hand side undertook that testing just purely using a jump mat or a contact mat. So they say that these tests are reliable, but we're actually only talking about a single metric here, which is jump height. And actually there's a lot more metrics that we can gather from jump testing nowadays. Equally, the standing broad jump appears to be very, very highly reliable according to Dugdale and Perez Castilla, but ultimately we're only talking about jump distance there being measured by a tape measure. So yes, these tests are typically quite reliable, all of them. However, we are only talking about a single metric of jump height, i.e. the outcome measure. And I think in this day and age, there's a lot more information that we can gather beyond purely outcome measures based data,
even if we don't have force plates. So we're going to start to dive into the jump testing with a little bit more of a critical eye now over the next 10 slides or so. So I wanted to start by offering a little bit of critique around the squat jump test. And this is a fantastic paper by Jeremy Shepherd in 2008, which was looking at essentially the usability of the squat jump in order for it to be purely a concentric only movement, which of course we know it should be. So for anyone who's unsure, the squat jump is where we typically ask our athletes to flex their hips and their knees to approximately a 90-degree knee angle, hold that position completely static before then asking them to jump. And we don't want to see any additional dip. The movement has to be purely concentric prior to takeoff. Now, this study that Jeremy Shepherd conducted showed that when this happens on force plates, you can see what they've highlighted here on the force trace is a small amplitude counter movement. That's what SACM means. So essentially, this force trace is showing that even when we give our athletes very, very clear instructions about making sure our movement is purely upwards and only concentric based in this test, we sometimes still get a small counter movement that actually the naked eye can't often see. And the reason the naked eye can't often see this is because, remember, in a counter movement jump, the movement starts with an unweighting phase. That is to say, we get meaningful changes in force before the human eye can actually see any movement occur. So it's actually very, very difficult to ensure that there's absolutely no dip or no counter movement in a squat jump test. And it's probably one of the reasons why I don't use it anymore, to be honest with you. And I wanted to use this slide to highlight that actually it's very difficult for the squat jump to be performed purely concentrically because often movement occurs that really we can't see properly. And just to give you context, this small amplitude counter movement on average resulted in a 4.6 centimeter increase in jump height, with the range being between 1.7 and 8.6 centimeters. So we are actually getting substantial increases in jump height as a result of these tiny little counter movements or dips that actually we might not be able to see very easily or at all. So I think, yes, the squat jump is reliable, but that probably means that actually these athletes are consistently performing a counter movement that we can't always see very well. And that defeats the purpose of using a test like this. So I just wanted to offer a word of caution about the squat jump and consider that actually maybe some other easier to perform jump tests might give us more reliable, accurate and usable information. So based off what we said about the squat jump, logically then the next test we should talk about is of course the counter movement jump, which is, for those who are unsure, just your regular vertical jump, if you like. And this is where we start standing upright. We dip more often than not to a self-selected depth and then try and jump as high as possible thereafter. So what you see on the left is our force trace, and I was talking on the previous slide about the unweighting phase, and here we've got our athletes standing perfectly still on the force plate for 2 seconds, which is represented by that straight line. And then we get our trace here, which is what this looks like just prior to takeoff. And when you see the black line 0, this is the time where, of course, the athlete is in the air because there is no ground reaction force. And this huge spike in force is where we get our initial landing. Now,
I've also included a table from an article in the NSCA Strength and Conditioning Journal by my colleague Shyam Chavda, which outlines some of the typical and also alternate type of variables or metrics that we can get if we do testing on a force plate. And of course, they range from a whole host of different metrics, looking at purely force, power, understanding the interaction between force and time, so looking at impulse, assessing velocity, and then also looking at some time orientated metrics as well, like eccentric and concentric duration. Now, it can be a little bit challenging knowing which type of metrics we should be looking at, but I think the main point here being that because the counter movement allows athletes to perform vertical jumping in a much more natural style of jumping based off what we've learned ever since a young age, it's a very simple, easy to perform assessment, and there's a whole host of different information that we can gather accurately, quickly and reliably using force plates. So the counter movement jump is, and it's probably one of the metrics that we see most commonly in research papers and in practice, and it's because it's so quick, simple and easy to perform. And we'll talk a little bit more in a few slides time about the relationship between the counter movement jump and some other independent measures of performance, which of course then provides that biological basis for why we should be using it as part of our test battery potentially. The next assessment to talk about is the drop jump, which I'm sure many of you will be familiar with. Now this figure comes from a technical model paper in the NSCA Strength and Conditioning Journal by Jason Pedley, and you can see that there's two types of jump being performed here. Now you can see A here, and this represents all these different figures across the top. Now this is being referred to as a depth jump in this table, and then B, all these figures underneath are being referred to as a drop jump. Now the key thing to focus on really is we're seeing quite a lot of bend or flexion in the hips and the knees upon landing in the depth jump, much less bend, of the hips and the knees on landing in the drop jump. And I think the point of showing you this is to show you how some of these different metrics that we often gather during drop jump testing varies, depending on what our focus or our test instructions are. So for the top row of images, the depth jump, you can see that actually if we compare jump height to the drop jump, he jumps much, much higher. But actually he jumps much higher, but for the sake of spending much, much longer on the floor, you can see that he's spending 0.4 seconds versus effectively half that time in the drop jump. Now, as a consequence of that, whilst jump height might be higher, reactive strength index, which is jump height divided by contact time, actually RSI, which is often the outcome measure used from drop jump testing, is actually much, much higher in the test where we don't jump as high, but actually we focus on getting off the ground as quickly as possible. So you can see that, yes, I jump about 7 centimeters higher, but I spend half the time on the floor in the drop jump in this second row of images. And ultimately, when I take my jump height and I divide by my contact time, we get a superior or higher reactive strength index score than if we allow our athletes as much time on the floor as possible to maximize jump height. And I think there's an important message here, and that is to say, if we drop off a box and we allow our athletes to bend their knees as much as they want and spend as much time on the floor before jumping as high again, we may as well just do a counter movement jump, because that's effectively what the counter movement jump is. So I think when we're performing the drop jump assessment, perhaps, and this is really just my opinion to be honest, but we should be focusing much more on being reactive, being stiff, spending less time on the floor, so that actually our body is acting like a true stiff spring. And that's why in this drop jump example here, we see much less time on the floor compared to jump A. And as a consequence of that, when we calculate stiffness, we see our stiffness metric is effectively 3 times higher than the depth jump. So there are advantages and disadvantages to both assessments. However, it's very clear in the depth jump to me that we're not really utilizing the stretch shortening cycle very effectively, because we're spending so much time on the floor, in which case we may as well just do a counter movement jump, to be honest, with depth jump A, and drop jump B is really focusing on being quick and stiff off the floor. And I think that's a better measure of stretch shortening cycle mechanics, to be honest. And the final jump assessment I said we'd focus on is the standing broad jump, which for anyone who's unsure is effectively just a long jump from a static stationary start. Now, this is a really good study that looked at the test-retest reliability of various different metrics when the assessment was conducted on a force plate, and also conducted unilaterally and bilaterally. So what the authors have done here is they have highlighted coefficient of variation values in this column and in this column for any metric where values are greater than 10%, which might showcase that there's potentially a little bit too much inconsistency in the data. And you can see there's a few metrics which show CV values higher than 10%, but not drastically higher. The interesting one, though, is mean power and peak power, which is very often metrics that are recorded in research and reported when running correlations with other measures of performance. Actually, mean power and peak power were a little bit noisy, okay, in the standing broad jump assessment. But generally speaking, we can see that velocity, force, and impulse, these metrics tend to be quite reliable, which is really good, which is really useful, and shows that we can gather some meaningful data when we conduct a standing broad jump assessment on a force plate beyond just jump distance, and that this type of data is usable because this is a between session reliability study. So after giving a brief overview of those 4 different types of jump assessments, I did mention that in this day and age, we should be able to gather more information than just purely outcome measures data. We should be able to get more than jump height. We should be able to get more than just jump distance. And I was referring, particularly in the counter movement jump and the standing broad jump slides, about the use of force plates. But I do acknowledge that not everyone will have access to a force plate, because not everyone has the budget for them. And so the question becomes, well, if I don't have force plates and I would like to use something beyond a jump mat or contact mat, what can I do? And this is, of course, where Carlos Balsalabra Fernandez's app, My Jump, which is actually now called My Jump Lab, is very useful. And he's developed, I'm sure I don't need to tell you, but he's developed a series of smartphone applications so that we can measure things like jump performance, change of direction performance, velocity during resistance training, range of motion at the ankle during a dorsiflexion assessment, so that people can start gathering data just by using their smartphone. Now, whilst I haven't included it in this presentation, the first thing to mention is in 2015, Carlos conducted a validation study for the first version of My Jump.
and essentially showed that the accuracy of the app against the force plate was nearly perfect, essentially showing that people can start measuring jump height with a smartphone app and it will give you very, very similar information to a force plate, which is very, very impressive, really, particularly when force plates can cost anywhere between sort of €1,000 all the way up to probably €20,000, and actually his app probably at the time only cost about €10. It was a very, very impressive study, and Carlos's work has really gone from strength to strength over the years. So I'm now going to talk about a recent validation study that we conducted using Carlos's most up-to-date jump app, which is called My Jump Lab, where we validated more than just jump height. So I approached Carlos probably a couple of years ago now and said, with the My Jump app, because you are now filming all the jumps to help to manually detect takeoff and landing, which of course then gives you flight time so that the app can work out jump height. I said, given that the app has to manually determine takeoff and landing, what is stopping you calculating the metric of time to takeoff or contraction time, depending on what you would call it? And of course, if we can get time to takeoff or contraction time calculated, then of course we can also calculate modified reactive strength index, RSI mod, because that is calculated as jump height divided by time to takeoff. So what we've got here in this study is we conducted about 20 or so sports science students. We filmed them using the My Jump Lab app, which is an upgrade from My Jump 2. And we also got them to make sure that those jumps were also conducted on a Hawkins Dynamics force plate. And what we see here is the raw scores for jump height, time to takeoff, and RSI mods. We've reported our reliability data for both measures, the force plate and the app. And then we've also reported the difference in scores as a Hedges G effect size data. And just to give you an indication, if you look at the key here, any effect size that is in bold indicates a statistically significant difference between the force plate and the app. So what we saw actually is that jump height was perfect. There was absolutely no difference. So this just reiterated what had already been done in Carlos's original 2015 validation study. Time to takeoff was quite different actually. So we saw I guess if our effect size scale, this is a moderate to large difference. We can see that on the force plate, time to takeoff on average was determined as just under 0.8 seconds, but in the app it determined contraction time or time to takeoff as considerably less time, 0.71 seconds. Now the reason for this is because on a force plate, the first meaningful change in force happens from something called an unweighting phase. And so essentially what that means is we get changes in force before the naked eye can actually start to see movement. So time will begin once the first meaningful change in force surpasses 5 standard deviations of the athlete's body mass when on the force plate. However, when we are watching a video, we can only start the time when we actually see movement occur, which is later than that first meaningful change in force. So that's why the time is much higher for the force plate than it is for the app. So what we did is we plotted our raw data like coordinates on a graph, and essentially then we were able to plot our y equals mx plus c equation. So we were able to apply what we call the correction factor or the correction equation to the raw time to take off scores. And if you then see, once we plotted that correction factor or that correction equation here, you can see that the difference was almost identical. So again, we turned a moderate to large difference or effect size into absolutely no difference whatsoever once we had applied that correction equation or that correction factor. Now that correction factor has been built into the algorithms of Carlos's app. And then what we do is we take our already accurate jump height score. We then take our correction factor applied time to take off measurement, and we divide that by jump height to give us an accurate modified RSI score. So you can see that we actually had a small to moderate difference in RSI mod on our raw scores, and the reason for that is because there was such a big difference in time to take off. So no difference in jump height divided by a large difference in time to take off results in a small to moderate difference in RSI mod. When we take no difference in jump height divided by no difference in time to take off, we get virtually no difference in RSI mod. And this correction factor has now been embedded into the time to take off metric in Carlos's My Jump app, so that practitioners can confidently gather jump height, time to take off, and RSI mod just from using his app now moving forwards. And that enables us to not just get the outcome measure of how high an athlete jumps, but it also gives us a little bit of an understanding of their strategy by looking at contraction time and modified RSI as well. So if you don't have a force plate, if you've got a very, very limited budget, we've now validated strategy-based metrics so that you can get more in-depth information from the counter movement jump. I'd also add as well that you can essentially do the same thing for the drop jump test as well using Carlos's app, because previous studies by Thomas Haynes and a few other people have shown that we can validate ground contact time, jump height was already validated, and in the same principle as we did in this study, if you can accurately determine jump height, if you can accurately determine ground contact time, then of course you can gather reactive strength index as well. So we've got really quite advanced use of Carlos's jump apps now to get more than just outcome measures data, and it's a really useful and viable option for those practitioners who don't have force plates or who have very limited budgets. So, as we mentioned earlier on in this presentation, one of the things that we need to consider is, do our tests correlate strongly with other measures of physical performance that we know are important for our athletes? So this is a study that focuses on female athletes specifically, and I've copied in two tables here, which is a series of correlation coefficients for high school and college football players respectively, and I've put our red arrows there so you can see which line we're interested in. But ultimately the counter movement jump, and this is looking at counter movement jump height only as the metric of interest, we can see that we've got moderate to large correlations with how fast athletes sprint, and we of course know how important this is because football players have to do repeated sprints on numerous occasions throughout training and competition. So in that top table there, we can see that the R values range from minus 0.491 all the way up to minus 0.58. And for college players, those correlations are a little bit larger, ranging from minus 0.658 all the way up to minus 0.788. Now, it's important to remember that these correlations are negative, and what that means is that the higher someone jumps, the faster these female soccer players are. And that's because the desirable outcome for a counter movement jump is the larger value. We want them to jump higher. But the desirable outcome for a sprint test is the smaller number, because a smaller number means that they completed the test in a shorter amount of time and therefore their velocity was higher. So negative correlations between jump tests and sprint tests, or jump tests and change of direction speed tests, are typically a good thing when the outcome measure for the speed and cod speed tests is time to completion. So ultimately this shows us that athletes who jump higher are typically faster during linear sprint tests. Now this is a similar study design but conducted in both male and female college players. And what you can see here is that 2 vertical jump tests were conducted. Okay, we had the squat jump and the counter movement jump. And then we've also got peak anaerobic power and power to watt ratio for both the counter movement jump and the squat jump. And these are being correlated against acceleration, top speed, and 2 different change of direction speed tests, the pro agility and the T test. We've got separate R values for male and females, M and F, and you can see that any correlation that's deemed statistically significant has an asterisk symbol next to it. And I guess if you scan the table, what you can see is there are a lot of asterisk values here. So the first thing to say is that when we look at the relationships between squat jump or counter movement jump and acceleration, we seem to have sort of moderate relationships ranging from -0.7 to -0.61. Again, remember these are negative correlations. The higher someone jumps or the more power they produce, the faster they are, because all of these tests, the outcome measure was time to completion. However, when we start looking at the relationships between these jump tests and maximal speed or top speed, we not only get much more consistent correlations, okay, but actually they're also a little bit higher as well. So they range from -0.45, but they go up to -0.68. So the magnitude of these correlations is a little bit higher. And then if we collectively scan the R values for both change of direction speed tests, it's similar. Okay, -0.45 being our lowest meaningful correlation, but this time extending up to -0.79 and -0.76. So generally speaking, we can say that there is consistency in meaningful correlations occurring between how high an athlete jumps and how fast they are at both acceleration, top speed, and change of direction speed. So that gives us a pretty strong foundation or basis for including jump tests as proxy measurements for linear and change of direction speed, which are of course physical characteristics that are so important for football players. And then to finish off this jump section, I thought I'd include this summary forest plot from this meta-analysis that we conducted looking at the association between RSI and independent measures of physical and sporting performance. And what you can see here is our summary effect size with confidence intervals between RSI and a number of different independent measures of physical performance here, ranging from endurance, strength, acceleration, top speed, and change of direction speed. What you see here on the right is our group or summary or pooled effect size, or R value, noting that the R value is the effect estimate. And I think it's important to outline here that firstly, many practitioners assume that the outcome measure of RSI is the metric we should be monitoring from drop jumping or rebound jump testing. But reactive strength, remember, is a ratio or an index. It's a product of how high someone jumps versus how fast they are off the floor. That makes it a ratio, and that might go some way to explaining why these correlation values are actually not as high as some of the correlations we saw between the counter movement jump and linear or change of direction speed. So you can see that, typically speaking, endurance performance is often classified by things like movement economy rather than time. So a positive correlation tells us that the higher someone's RSI value, the better their movement or running economy. Again, if we look at our correlations with our 3 strength measures, this tells us that the higher the RSI, the higher the strength value, whether that's isotonically, isometrically, or pooled strength measures. But it's important to note these values are not particularly high. 0.356, 0.339. These are weak correlations, and the only reason that they are statistically significant is because we have a large sample size for a number of studies that have investigated this particular type of study. When we look at the correlations between RSI and linear speed, again, negative correlations showing that higher RSI values are associated with faster athletes. But again, these are weak correlations. It's only when we get to change of direction speed that we actually get a moderate correlation value. So this is slightly higher between RSI and change of direction speed. Once again, negative, higher RSI means faster change of direction speed times. But I think it's important to outline that these correlations range from 0.33 weak to minus 0.565, which is only moderate. We don't really have any large correlations here, and we're only bordering on approaching large correlations. Generally, these are typically quite small, and the reason for that is probably because we have raw data in terms of something like movement economy, newtons for isometric strength, or kilograms lifted for strength, or time for top speed, time for acceleration, or time for change of direction speed. These are all raw outcome measures based data, but they are being correlated with reactive strength index, and the reactive strength index is a ratio, and that means it's made up of 2 component parts. And something that is made up of 2 component parts is typically more noisy or more variable than the component parts or the outcome measures themselves. So when you run a correlation between a ratio and a singular stable performance metric, it's hard to get a very, very large correlation. So I think practitioners need to be aware that drop jumping as a test or rebound jumping as an assessment method is good, and it's fine because that gives us an understanding of their reactive strength or an athlete's reactive strength. But the reactive strength index as a metric is a ratio. And there are problems with ratios because we create one single value when it's actually made up of 2 component parts or 2 sources of information. So remember that it's all about the metrics that we choose from the tests, and not just relying purely on what lots of studies and what lots of practitioners have done historically. And I think that RSI as a metric, because it's a ratio, has its limitations. As you can see from these small to moderate correlations, with other measures of physical performance. So the next physical capacity that we'll focus on now in this presentation is linear and curved sprinting. And the concept of investigating curved sprinting has only really come into the research world probably in the last sort of 5 or 6 years, something like that. But it's a really important physical characteristic that we need to consider, because historically we have defined sprinting via linear sprints or change of direction sprints, assuming that when athletes perform a change of direction, it's done with a very, very specific cutting action. But actually, if we view video analysis of football players during competition and matches, it's quite often arced or curved sprints that take place, particularly for playing positions like centre forwards when they are trying to time their runs to beat an offside trap, for example. So this is a study that looked at the prevalence of how much sprinting and in what volume or magnitude of distance sprinting occurs across the different outfield playing positions in football. So this is a total of 147 players included across 10 matches during the 2008 to 2009 and 2010 to 2011 Europa League competitions. And what we can see here for this first figure on the left-hand side is that sprinting has been classified by distance as 0 to 10, 10 to 20, and then greater than 20 meters. And it's looking at the total number of sprints performed by these different outfield playing positions. And what we can see is, typically speaking, that 10 to 20 or greater than 20 meters as the number of sprints performing in a game happen much, much more than the shorter distances of 0 to 10. If we break it down via playing position, typically we can see that our forwards, our centre forwards, produce the greatest number of sprints in games, which if we start thinking about the demand of that playing position, it's probably not a huge surprise. And then central defenders and central midfielders typically sprint the least number of times. If we move to the graph on the right and we then translate that total number of sprints into total sprint distance, again, it's not a huge surprise to see our forwards have the largest total sprint distance, given they typically are doing the largest total number of sprints. And this tiny little square inside our box plot here shows that on average the total sprint distance is just under 400 meters, okay, per match, whereas our central midfielders and our central defenders are actually doing just under or just over half that at just under 200 meters. So this gives us an understanding that we're getting on average somewhere between sort of 7 to 7.5 number of maximal effort sprints per game, but with a total distance coverage ranging from 200 to 400 meters. Now that doesn't sound like a huge amount when we consider that across a 90-minute football match. However, we need to be able to contextualize that information with the ability to recover, the ability to be in the right position during important moments in matches, blend that type of data with the vast number of changes of directions that occur in a match. And when we put all of this physical requirements together, there's quite a high stress and load that football players are required to tolerate during matches. If we start trying to understand curve sprinting in football now, Now, I don't think there's an awful lot of data looking at the prevalence or the amount of curve sprinting, or even how it is classified during competition in football. But I did find this excellent study that tried to quantify some of the ground contact times in relation to linear sprinting here. So when we're doing curve sprinting assessment, which is typically done using either the curve on the centre circle in a football pitch or on the edge of the penalty box. So what we see here is that for these particular football players, we've got ground contact times, okay, during a 17-meter linear sprint of around about 0.13 to 0.14. So good, we're talking about very, very fast stretch shortening cycle mechanics here. And when we relate that to curve sprinting, either to the right or to the left, we see a real marked difference between limbs here. You can see that if I curve sprint to the right, my right foot, which serves as my inside leg when I curve sprint to the right, spends much, much longer on the floor relative to the outside leg. In fact, the outside leg, the ground contact time is very, very similar to when I'm running in a straight line. But my inside leg is having to spend a great deal more time on the floor, ultimately applying braking forces to some degree in comparison to the outside leg. And those braking forces are needed in order to be able to maintain that arc or that curve. This data is almost perfectly represented when we curve sprint to the left as well, noting that if I now change direction, my inside leg becomes my left foot, not my right foot, and you can see that this data mirrors exactly what happens to the inside leg in the opposite direction. And so too does the outside leg. We're getting almost identical data regardless of which direction we curve sprint in. But the main point is that our outside leg is able to maintain very similar ground contact times to running in a straight line, but our inside foot has to spend longer on the floor to apply a little bit of additional braking impulse or braking force so that we can continue to run on an arc or on a curve. And this gives us an important neuromuscular characteristic of curve sprinting, noting that if I spend longer on the ground and I'm going to have to apply a larger amount of braking forces with the inside leg relative to my direction of travel, that will have a greater stress, strain and load on that inside leg because of the higher degree of braking forces. So that's something to consider within the context of curve or curvilinear sprinting. So once we know and understand the prevalence of linear and curve sprinting in soccer, and we understand some of the key characteristics, it's of course, as I have done throughout this presentation, important to know that what we are assessing is both valid and reliable. So given that there are a very, very high number of studies that have reported reliability and validity of sprint testing in football players or soccer athletes, I thought it would just be useful to present a summary slide from a systematic review that's been previously conducted. And what we see here is we get characteristics of these studies, noting the N number, whether they were male or female, their mean age range, what type of level these athletes were playing at, the different sprint tests that were being considered, whether we were looking at inter, which is between session, or intra, within session reliability, And then in our final column here, we've got some reliability data as well. And remembering our ICC and CV scales, if we scan through this particular column, which is just a snapshot from this systematic review, we can see that our lowest ICC value, I think, is 0.8, and our highest CV value, noting that it's not reported in every study, is 2.3. So generally speaking, consistency as measured through the coefficient of variation is very good, with all values less than 2.3, and ICCs all being above 0.8 typically indicate that these tests are either show good or excellent reliability and very, very good consistency from the CV. Now, that's because we are typically measuring time, okay, the time taken to complete these tests, and time tends to be a very, very stable performance metric. So with that in mind, it's fair to say that linear sprint tests, when we measure time to completion, is a highly reliable metric, and that gives us confidence that we can use this data between test sessions and part of the routine ongoing monitoring process. And because curve sprinting is a relatively new concept within the field of sports science and strength and conditioning, I think it's expected that there isn't, to my knowledge, a systematic review looking at the reliability of curve sprinting, and that's probably because there aren't enough studies that have been done yet. But what we see in this particular study, they were looking at the reliability, or the between session reliability, excuse me, for different distance curve sprinting. CSRS means curve sprinting to the right side, and this means curve sprinting to the left side. And we've got that for different distances, 8.5 and 17 meters. And those reliability values and raw data values are then compared to linear sprinting, 8.5 and 17 meters as well. So if we look across to our ICC and our CV scores, we can see that for our linear sprints, we've got 0.89 to 0.96. So again, highly reliable with very, very low coefficient of variation, as we would expect. If we now take the first 4 rows of data, which correspond to our curve sprinting to the right and left sides respectively, we can see that our ICCs range from 0.75 to 0.93. So again, relative reliability ranging from good to excellent, and also with very, very low CV values, all values lower than 1.74. So we've got some confidence now that when we're assessing reliability between test sessions, we get very, very good consistency as measured by the coefficient of variation, and pretty high relative reliability as measured through the ICC as well. So similar to our linear sprints, that gives us confidence that when we're measuring time to completion in these curve sprint tests, we can use that data for further analysis. Now, given I've already presented some relationships between jump height and how fast athletes sprint, it stands to reason that I don't need to present that information again, just in reverse, because the relationship between the counter movement jump and how fast an athlete runs is exactly the same as the relationship between how fast an athlete runs and how high they jump. So we've seen from the jump section that there's a moderate to strong relationship between jump testing and how fast these football players typically sprint. However, I thought I would include some relationships between curve sprinting time and linear sprints and vertical jump performance, because we haven't presented that information so far, and this gives us a nice basis to understand whether or not there's a foundation for including curve sprinting in our test battery, noting that actually we haven't been able to determine whether or not there's a biological foundation for determining it yet. We've only just established that it's reliable. That's it so far. So this figure, which is presented really nicely on the left-hand side, gives us some correlational values between curve sprint velocity, so not time, we're talking about the metric of velocity now on the vertical axis in all 6 graphs, and velocity during linear sprinting at 5 meters, 10 meters, and 17 meters on the good side, which would be the fastest side, and the weaker side, which would be the slower side. So these 3 vertical graphs here with green individual data points represent the good side, the red points represent the weaker side, and the vertical axis is always curve sprint velocity, and that is being correlated against velocity at 5, 10, and 17 meters. And you can just about make out our R values here. We can see the R value between curve sprint velocity and velocity at 5 meters is 0.76 and 0.52, indicating higher velocity during curve sprinting is associated with higher velocity when you run in a straight line for 5 meters. That R value is 0.80 and 0.60 respectively for 10 meters, and then 0.82 and 0.74 for 17 meters. And 17 meters was chosen as a linear speed time to match the curve sprint distance that these athletes conducted. So with R values ranging from 0.52 to 0.82, there's a pretty strong and somewhat expected correlation between the speed that you go at in a curve sprint test and the speed that you produce in a linear sprint test. If we move across to table 2 now, we can see that velocity during the curve sprint test on the good side and the weak side was also being correlated with how high athletes jump on the squat jump and counter movement jump test. And again, we can see our values here ranging from 0.52 to 0.61, remembering that our outcome metric is velocity, not time. So this means higher velocity is associated with higher jump heights, and those correlations are just about large for each of the tests and each of the curve sprint sides. So we've got a pretty strong basis here that the velocity that you produce during curve sprinting is going to be strongly linked to the velocity that you produce when you run in a straight line, and it's also associated quite strongly with how high you jump. So we now have a reliable data that is strongly linked to these other important independent measures of physical performance that we know we should be tracking in football players. So there's a pretty reasonable basis now for including curve sprinting in our test battery for football players. So the next physical characteristic that we'll focus on is change of direction speed, and I'll only be focusing on this particular physical capacity in the field. Now, there's been some phenomenal literature come out in the last 10 to 15 years on COD speed, and I'm sure many of you listening will know that there's a number of different change of direction speed tests that we can utilize to assess COD performance in our athletes, and we've put a few of those examples here on this slide, such as the 505 test, the Illinois, the Arrowhead agility test, and the Pro agility test here. And really, practitioners should try and consider which one they deem most appropriate for their players relative to the movement demands that they have quantified during competition. Okay, when we think about change of direction speed and indeed agility, there are some phenomenal practitioners out there, such as Warren Young and Sophia Nymphius, who've created some really high profile, high quality research over the years. But I suppose in the last 5 or 6 years, the name that really springs to mind for me is Thomas dos Santos, who is from the UK and works up at a university in Manchester. And he's produced some absolutely outstanding research, practically applied research, looking at the prevalence of change of direction speed during competition in Premier League players. He's also looked at some of the more intricate neuromuscular qualities and characteristics of change of direction actions, which we'll look at on the next slide in football players, and also produced some real high quality review articles in journals such as Sports Medicine, outlining key fundamental considerations and qualities that practitioners need to remember when we're trying to assess this particular component of fitness. So this particular study looked at what are the meaningful turning demands of match play during competition of an English Premier League soccer team. And this data was conducted over 18 matches during the 2020-2021 competitive Premier League season. And what you see is there's 4 different graphs here. The graph top left, A, is looking at the total amount of turns that are typically conducted by fullbacks, centre-backs, wide midfielders, centre midfielders and centre forwards. Those turns have then been classified as small or low turns, and that is determined by the angles ranging from 20 to 59 degrees that the actual turn or change of direction happens by. A moderate turn is classified by 60 to 119 degrees, and then high turns or large change of directions classified as 120 to 180 degrees. And we can see, if you just look, we've got mean box plots here for each playing position with individual data points tracked over the top by those white markers there. And what we can see is that the highest amount of turning or change of direction happens, quite significantly happens for central midfielders here. As you can see, we see on average total number of turns per match or significant turning demands typically is just under 40 per competitive match. And then we can see that centre forwards and centre backs typically produce the least. Now, given that central midfielders typically produce the most amount of total turns in any given competitive match, it stands to reason that they also produce the most amount of turns when classified by low, medium and high COD actions. So you can see that the prevalence of change of direction actions per match is actually significantly higher than the data that we showed you for linear sprints, which ranged from the total number of meaningful sprints at a given distance ranged from around about 7 to 8 for different playing positions. Now we're talking about the total number of meaningful change of direction actions or turning demands is up at around about 40 per match. So we can see that sprinting and change of direction speed are of course both very important for footballers, but the prevalence of COD actions is much, much greater. Now this is another study conducted by Thomas dos Santos, and this looked at what happens to change of direction biomechanics when our angle changes during change of direction actions. Now there's a lot of data here, so I'll do my best to explain this relatively simply and concisely. Let's start looking at this figure on the left, which contains 4 individual graphs. Okay, this top left graph, or graph A, which is quite hard to see there, is ground contact time. This one on the right here is approach velocity. This figure bottom left is velocity at final foot contact, and this figure bottom right is exit velocity. Okay, so we've got ground contact time, approach velocity, velocity at final foot contact, and exit velocity. And these metrics are being looked at during a 45-degree change of direction cut, a 90-degree change of direction task, and a 180-degree change of direction task. So if we look just here, we can see that the amount of time we need to spend on the floor is much, much greater during a 180-degree cut compared to 90 and 45. So as the angle becomes less, we can spend less time on the floor, and probably because we are able to maintain our velocity. And essentially what you would expect is a mirror image of that for approach velocity, velocity at final foot contact, and exit velocity. Bearing in mind now that with the metric of velocity for these three graphs being the desirable outcome being the higher number, it's expected that velocity will be greater during a 45-degree cut compared to 90 and 180. And you can see that these two graphs are also the same trend or pattern. And that's because when the angle of cut is shallow, like 45 degrees, we're able to somewhat maintain our velocity. We don't have to apply a large amount of braking forces. Whereas for 90 and 180 degrees, where those angles are much, much greater, we have to apply much higher braking forces, which then results in a very definitive cutting action. Whereas at 45 degrees, we might have to apply a little bit of braking forces, but we can probably do a better job of maintaining our velocity relative to the straight line sprinting. If we now go to our second graph, this first graph here is looking at peak knee abduction moment. Second one here is peak knee internal rotation moment. This one is peak knee flexion. And this last one is peak knee abduction angle. Now the results are a little bit more complex, but ultimately, certainly for peak knee abduction moment and peak knee internal rotation moment, actually we get the highest abduction and internal rotation moments, the highest peak knee abduction moment during 90 degrees, not 180 degrees, and the lowest peak knee internal rotation moment, with this metric being a mirror image of abduction moment. Now, the reason abduction moment is highest at 90 degrees is because we have to plant our foot and cut in a very specific lateral direction, which of course means that we're looking at the angle of the knee relative to our center of mass. And when we have to plant our foot and cut laterally, that creates a very, very high abduction moment when our center of mass moves laterally relative to our knee joint. However, at 180 degrees, although the turning demand is much, much greater, or the angle is much, much greater, in reality, when we change direction 180 degrees, the chances are is that we've already orientated our body to travel in the direction that we then want to subsequently go in. So we get slightly less knee abduction moment because the angle is so great that we have to reorientate our body position before we do the change of direction itself, because the angle is so large. Now, peak knee internal rotation moment is a mirror image of that, as you can see. However, when we start looking at things like peak knee flexion moment and peak knee abduction angle, unsurprisingly, the amount we need to bend our knee is much, much, much lower. The moment, is much, much lower for 180 degrees, because this is effectively where we have to bend our knees the most, because the angle is the greatest, which means we have to apply the largest amount of braking forces at this angle. And that is reflected in the fact that our velocity is lowest when the angle is at its largest cut. So we've got some really, really high quality, thorough, in-depth information here. And I think what we need to, some of the key information to establish is velocity and the time that we spend on the floor will get slower and increase respectively as the angle of cut increases. And we need to be mindful of knee abduction moments being higher, not at 180 degrees, but typically at 90 degrees. That's because during that particular change of direction, the angle requires us to move laterally, where in contrast for 180 degrees, we've probably already orientated our body to start facing in the direction of travel. So I mentioned previously that Thomas dos Santos had also conducted one or two fantastic articles in Sports Medicine, journal which for the most part publishes meta-analyses, systematic reviews, narrative reviews. And this is a fantastic narrative review from Tom and his team looking at the effect of angle and velocity on change of direction biomechanics. And as the title very aptly names, there is an angle velocity trade-off. And I think this figure provides a really nice, clear summary of a traffic light system that practitioners can consider employing during training sessions for different change of direction tasks relative to a desired outcome being achieved. So what I mean by that is when we've got relatively small angles being focused on during training, 0 to 45 degrees, as we saw from Tom's previous research, velocity is quite easy to maintain. Ground contact time is relatively short compared to larger angle changes, and therefore we can instruct our athletes to try and maintain velocity. We don't need to focus too much on braking requirements. We can get them to just complete the task as fast as possible, knowing that things like knee abduction moments are not so high in this task. However, as the angles get bigger and we start focusing beyond things like 60 degrees, naturally, as the angle becomes greater, we have to apply more braking forces so that we can effectively move in the required direction, whether that be 60 degrees, 90 degrees, 135 or 180. So this visual outlines that as our angle changes, or as our change of direction angle, increases, we need to apply much greater braking forces and braking strategies prior to the actual directional change, and that's signified by the red, amber and green system. So a really, really nice, practically applied, meaningful figure for how coaches can consider coaching their athletes depending on the angle that's being worked on in training. So now let's start considering some of the reliability elements of these different change of direction speed tests. And you can see here in this first table on the left, we've got a number of different change of direction speed tests being looked at. The key is at the bottom of the table here. So you can see the first one is the T test. Second one is our slalom test. Then we've got a sprint 4 times 5 meters. Then we've got a sprint with 90-degree changes of direction or 90-degree turns. Then we've got sprint of different distances with 180-degree turns. And then we've got a sprint of different distances with forwards and backwards running. And you can see we've got 3 trials for each test with summary or mean data presented at the bottom of each one. And if we then look across for our ICC values and our CV values, you can see that all ICCs are well above 0.9, which tells us that relative reliability for these COD speed tests are very good or excellent. And our CV values, the highest value here is 5.6. So again, generally pretty acceptable levels of consistency through the coefficient of variation. I've also included this other table from the same study which tries to outline whether or not some of these tests are sensitive at being able to detect differences between playing positions. And you can see that if we start looking at the S90 and the slalom test and the sprint 4x5 meters, there's no meaningful differences in the times between playing positions. However, the T-test, we can see that defenders are substantially faster than midfielders and attackers at performing the T-test, and that when we also consider our sprint with backwards and forwards running and 180-degree turns, we can see that we do have some meaningful differences between midfielders and attackers. So this tells us that actually not all tests are created equal in terms of their sensitivity at detecting change or differences between playing positions. I also think it stands to reason that defenders are the fastest over the T-test specifically, because actually the T-test involves quite a lot of lateral movement, and defenders are quite often having to perform more lateral based movements than forwards and attackers when they are man marking and when they are jockeying for different positions and tracking opponents. Now this is one of my favorite change of direction speed research papers ever to date, actually. So this is a study by someone called Ruisi, and essentially what they were looking at was test-retest reliability of bypassing and sidestepping. Now what we mean by that is bypassing is essentially where I guess it's a bit more like a curved sprint, whereas sidestepping would be if I wanted to change direction 45 degrees to the right, I would specifically plant my left foot and push off in that direction, whereas bypassing would be running around this point, not employing a specific plant and cut, but taking a bit more of a curvedy linear approach to the change of direction task. And this is really simple in design, actually. We've just got a linear 10-meter sprint, but 10-meter sprint overlapped in different directions. And ultimately what you get is a straight line 10-meter sprint. You get 5 meters with a 5-meter change of direction at 45 degrees in both directions. 5 meters and then another 5-meter change of direction, this time at 90 degrees in both directions. The same for 135. And of course, if you wanted to do a 180-degree turn, you would just sprint to this middle point and run back. So you can see that they've got timing gates at the end of each point, noting that the start is here, but the end is at each position, depending on whether you push off on the dominant or non-dominant limb and whether or not you're doing bypassing or sidestepping. So it's really quite a flexible approach to assessing change of direction performance. And here you can see we've got the reliability of all these different angles, and as well as maximal voluntary isometric contraction of the hip abductors, knee flexors and knee extensors. But we're not so much interested in this data at the bottom. We're more interested in the reliability values, our ICCs, for these different change of direction speed angles here. And you can see that our ICC values are all considered excellent. We've got our 95% confidence intervals here. You can see that the lowest value, the lower boundary of the confidence interval, ranges from 0.85 to 0.84. That tells you that if the lowest value of the confidence interval is still good, the actual mean ICC value is all excellent. Coefficient of variations reported as well. You can see all of these values are well under 5%, showing very, very good consistency in the time taken to perform all of these different changes of direction on both dominant and non-dominant limbs, whether you're performing a bypass or a specific sidestep cutting action. So a very simple but effective study design, and it seems once again that when our outcome measure is time, you can see all of these are measured in seconds, the data tends to be very, very reliable, making it highly usable in practice, which is great to see. So similar to what I said for the linear speed section, given that we've already reported some relationships between jump performance and change of direction speed times, I didn't want to focus this section on relationships between change of direction speed and other independent measures of performance, because we've already done that throughout this presentation. Instead, I thought I would take Tom Dos Santos's final PhD study, which looked at how we can effect change of direction technique through specific coaching interventions. It's a really difficult study to conduct, and I think Tom's done an absolutely incredible job. So we've got a schematic or a figure here of the study design. So the first 2 weeks were taken for testing, and he was looking at 45 and 90-degree cutting performance using 3D motion analysis. Tom managed to recruit 30 men. Now, they weren't all from football, but some of them had a history of competing in the sport. 16 for the intervention group and 14 for the control group initially. I'll come back to the training intervention in a minute, because that's what this table is here for. There was a couple of withdrawals from the intervention and the control group, meaning that by the time he got to post-testing, there was only 15 in the intervention group and 12 in the control group. But essentially, we had a 6-week technique modification intervention for the intervention group only. And there were 3 real things in this technique modification that Tom was trying to focus on. First and foremost, he was trying to get these athletes to adopt a penultimate foot contact dominant braking strategy. So ultimately, the reason for this is because if we apply more force just before the actual change of direction, typically this is associated with faster COD performance. Secondly, Tom wanted to make sure that he was focusing on the ability to express force during that propulsive phase, so as these athletes are changing direction during the frontal plane. So that's particularly important at 90 degrees, where the angle of cut is larger, and we of course initially move laterally straight after the change of direction. And the reason for this is that to enhance our mediolateral propulsive force expression, we want to be able to do that by facilitating shorter ground contact times and a more effective body position, which is where the lower limb frontal plane control aspect comes into it. And then of course the third aspect was not forgetting the trunk, because a lot of what our body does will be dependent on what our head and our trunk do. So this final coaching focus asked athletes to face towards the direction of travel, and that was so that our body was leaning in the intended direction that we wanted to move. So these 3 aspects were focused on during the 6-week intervention, and Tom looked at a very wide range of performance and biomechanical measures to see whether actively coaching to try and improve change of direction performance not only improved how fast they do it, but some other important metrics as well. And that's what the next two slides are going to focus on now, those results. So Tom looked at quite a wide array of different variables and metrics during these 45 and 90-degree cutting tasks. And I've only just presented a handful here, just to try and showcase my point. So this is a table of results purely for the 45-degree cutting action. And you can see that we've reported data for total time, or how long it takes them to perform the 45-degree cut, ground contact time, exit velocity, knee flexion and ankle dorsiflexion, and we've got data for the intervention group IG and the control group CG. Here we've got our pre and post values, and we're looking at within group changes, and you can see that any value that's highlighted in bold, any effect size value, represents a significant or meaningful change. Now for these 5 metrics, we can very clearly see where the benefit lies. Ultimately, if you do nothing and you serve as part of the control group, you get effectively no change in your performance. However, the intervention group that was subject to Tom's coaching, you can see, are noticeably faster at performing the task. They spend a little bit less time on the floor, which naturally contributes to their ability to propel themselves propulsively in the correct direction of travel. Exit velocity is substantially higher. Remember, this is velocity, not time. This is about how fast they move. So the desirable outcome is the larger value. And you can see we've got an effect size, a very large effect size of 0.96, showing that they are moving faster once they have come out of that 45-degree cutting action. The amount of knee flexion is less, so they are bending their knees to less of a degree after they have conducted Tom's intervention, which shows us that if there is less joint displacement, that's probably a reason why they are spending a little bit less time on the floor, why they are moving quicker, and why they take less time to complete the task. And that's also reflected in ankle dorsiflexion joint range of motion too. Slightly less ankle dorsiflexion range of motion, but from a joint perspective, most of the benefit is seen by reducing the amount of flexion at the knee. So clearly this coaching-based intervention is very, very effective at not just improving how fast they complete the task, but some of these more in-depth biomechanical measures as well. And we'll also now have a look at the effectiveness of this for the 90-degree cutting task as well. So similar results seen for the 90-degree cut, although not completely identical. We see that the intervention group are substantially faster at performing the task. Actually, there's no meaningful change in ground contact time this time, although they are still 0.01 second faster. Exit velocity again shows a moderate to large improvement. Again, the control group show no change in any of these variables. Knee flexion, once again, we get an improvement in knee flexion, and by improvement, I mean we get less knee flexion, which probably contributes to greater exit velocity and ultimately completing the task faster. Surprisingly though, we actually got a greater ankle dorsiflexion, okay, which means, and I think it's quite hard to explain that outcome actually, because the knee is essentially a byproduct of what goes on at the hip and the ankle, given how that joint is built. It's difficult to understand how you would get much greater ankle dorsiflexion without some degree of increased knee flexion. That probably means that these athletes were performing a much more upright movement pattern during the 90-degree task. And I'm not sure that lots more ankle dorsiflexion is entirely what we would want. But what I can tell you is they are still performing the task faster. they are still performing the task with less knee flexion, and that's ultimately contributing to greater exit velocity. So in summary, it appears that this particular coaching intervention that Tom conducted was very, very effective at improving overall change of direction performance at more than just one different COD angle. And that shows us that focusing on the penultimate foot contact, getting our athletes posturally into the correct position, and then focusing on strong expression of force in the direction of travel can have a really meaningful impact on the outcome of COD performance. So we shouldn't just be focusing on physical characteristics alone. So the next physical characteristic that we will look at is repeated sprint ability, and similar to linear sprint and change of direction speed, will only focus on assessments in the field to try and retain some ecological validity for the sport. Okay, so understanding this particular physical characteristic might be a little bit less common knowledge than some of the other performance metrics like jumping or sprinting for some practitioners potentially. So when we consider which tests can we use to assess or determine repeated sprint ability, I think that practitioners are somewhat dictated by their own creativity and what they can come up with. So there's lots of different examples in the literature, such as 6 times 40 meter sprints, 6 times 40 meter sprints, but split with a 180-degree change of direction, so a 20 plus 20 meters, 8 by 25, 8 by 25 with 90-degree changes of direction after 12.5 meters. So I think that practitioners can somewhat come up with their own, and how we would do that is ultimately be guided by the demands of the sport. And so this means us understanding the movement patterns that players are accustomed to during competition and training. We would of course get that information via GPS, and having a really in-depth understanding of things like volume, duration, distance of sprints, understanding how this differs during competitions, such as looking at differences in movement characteristics between first half and second half, and also understanding some contextual information as well, such as looking at how volume, duration, and distance changes with and without the possession of the ball. And once we have that information, perhaps then we can think about designing a repeated sprint protocol that is, one, reliable, but two, also somewhat a reflection of the type of sprint distances and repeated sprint demands that players are exposed to during competition and training. So this was a study conducted in elite female players, and we've got a schematic here showing the repeated sprint protocol, which I'll describe in a minute. We've got the ability of the test and the metrics gathered, their sensitivity at detecting change between national and state level players, and then some reliability data for the outcome measures too. So if we start looking at this particular test, you'll notice from the key, the solid line indicates sprinting. The very small dotted line indicates a deceleration zone. And then the bigger dashed line would indicate a jog. Now what we have here, excuse me, is effectively jogging through this particular 5 meter period, turning round a cone, jogging again. Once we hit this 10 meter mark, sprinting 20 meters as fast as we can, and then effectively repeating that process. Okay, so we get sprint for 20 meters, and we also get a total jogging distance that also includes a change of direction for a total of 10 meters at both ends. And this is just a protocol that is then repeated. And what we see is we're assessing the initial 20-meter time, the total time for the amount of protocols or repeated sprints that were conducted, and we get what's called a decrement in time that's expressed as a percentage. And we can see that there's no meaningful difference in the decrement metric between national level players and state players, because we've got a p-value of 0.49. That would need to be less than 0.05 for it to be deemed statistically significant. However, we do see that national level players are actually faster, significantly faster than state level players, and their total time performing the repeated sprint protocol is considerably less. So not only are they faster, but their ability to maintain speed repeatedly is also significantly better. So we've got a very simple repeated sprint design. It's got an ability to discriminate between playing levels. And then lastly, if we look at the reliability here, looking at test 1 versus test 2, we see between session reliability for total time and the percentage decrement and typical error, okay, which is expressed as a percentage. So this would be very similar to the coefficient of variation. We can see that total time shows excellent reliability, but actually the percentage decrement does not. So we should probably be a little bit mindful about using percentage decrements as a metric, given that A, it's not very reliable, and it's also not able to discriminate between playing levels. This study looked at the reliability of a slightly different repeated sprint test, but claimed it was also soccer specific. So if we start with the figure here and we follow the solid black line, we can see that they initially sprint 10 meters, then they have to sprint with a directional change, another directional change, sprint a further 10 meters, and then our dotted line showcases just a recovery period by jogging back round to the start position and then repeating the protocol another 5 times. So I'm not entirely sure what makes this particular protocol soccer specific, given that probably any team sport will be required to undertake various different magnitudes and volumes of changes of direction. But what they have done nicely in this table is outline the time for 7 subjects across 6 different trials here, and we've got our mean data and our standard deviation and our coefficient of variation, this time for each individual subject. And I really like this study because we get to see the trial to trial consistency of the data for each individual rather than as a group. And you can see that our CV values never go higher than 3.3, showing that basically across these 7 athletes, we tend to get very, very specific and accurate sprint ability readings. But it's important to outline that the reason we probably don't get a very large change in sprint times for any of these athletes is because there is quite a large amount of time spent actively jogging during the recovery. There is a greater distance. So if we see we've got 10 meters here and then essentially another 40 meters or so jogging back, we've got a little bit over 50 meters of active jogging time compared to the full 30-meter sprinting distance. So the reason we probably get these consistency is because enough time is spent doing our active recovery prior to the next trial. Now that's great, and that enables us to assess maximal sprinting ability repeatedly, but that is not quite the same as repeated sprinting that deliberately tries to invoke acute fatigue and an accumulation of blood lactate concentration. And that is sometimes done because we are trying to improve an athlete's ability to buffer against lactate. So I think that's probably why this protocol is potentially not necessarily soccer specific, because arguably too much time is being spent doing an active recovery or jogging before the next trial in order to invoke a true high blood lactate concentration response. So remember, once we know that our tests are valid, reliable, and usable, we're trying to establish whether or not there's a strong link with other important measures of physical performance. So this is a good study because it was conducted in professional players, and it's assessing the link or the association between repeated sprint ability and aerobic capacity. Now, I haven't assessed or discussed aerobic capacity in this presentation yet. That will be the final physical characteristic that we discuss after this. So this figure has two graphs, as you can see, 1A and 1B. 1A is looking at the mean sprint time obtained from repeated sprint protocols in seconds and the association with relative VO2 max. And 1B is not looking at mean but total sprint time in seconds and its association with VO2 max. And we can see from 41 professional players, this R value ranges from minus 0.67 to minus 0.59. So we've got quite a large correlation between repeat sprint ability and aerobic capacity. And very simply, hopefully you can see what that means, is that if you want to score higher on your aerobic capacity, it tends to be associated with spending less time sprinting, i.e. you are faster. Okay, remember, we've got a negative correlation here because the desirable outcome on the vertical axis is the smaller value because it's an outcome measure of time when running. And the desirable outcome for aerobic capacity on our horizontal axis is a bigger number. So ultimately, what we want to see is a negative correlation if there's a meaningful association between repeat sprint ability and aerobic capacity. And unsurprisingly, in professional players there is, and that's probably because the greater their aerobic capacity, they have a higher tolerance or ability to not only buffer against lactate, but also recover in between sprints, which then enables them to perform more subsequent repeated sprint bouts. And I've chosen this study because of its ability to discriminate between playing levels. So this is looking at repeated sprint ability in professionals versus amateurs. And what we see here in table 1 on the left is a whole host of different metrics looking at the best and the mean score during repeated sprint ability and the percentage decrement. We're then also looking at a whole host of different physiological based metrics gathered from a high intensity training session. So H+, if you refer back to the key down here, is our blood hydrogen ion concentration. Our HCO3 is our blood bicarbonate concentration. La+ is, of course, our blood lactate levels. HR mean is our mean heart rate, and then RPE is our rating of perceived exertion. And our cardiorespiratory measurements is primarily looking at the time constant and aerobic capacity as measured by maximal oxygen uptake, which is our VO2 max. We've got data here for professionals, amateurs, and then very helpfully we've got our effect size values in the final column. And if you just look at the raw data, we can see that unsurprisingly, professionals show pretty much moderate to large differences between amateurs for almost all of our metrics. And if we then look back at the raw values in these first two columns, we can see that our scores for repeated sprint ability are much lower for professionals. And if we then sort of translate that back to VO2 max, we can see that's because they've got a moderately better VO2 max score. So unsurprisingly, with a better VO2 max, provides professionals with a better ability to recover in between repeated sprint bouts, which enables them to achieve better scores, both from best mean and percentage decrement. So we've got a protocol or a test measure in repeated sprinting that is able to discriminate between playing levels, which is useful. And then table 2 here is looking at the association or the correlation between our repeated sprint ability metrics, which is best time, mean time, and percentage decrements, with some of these high intensity training measures that we mentioned in table 1. Okay, so again, just refer back to your key for blood hydrogen ion concentration, blood bicarbonate concentration, blood lactate, VO2 max, and of course our time constant. And I guess the key thing to pick out without focusing on every single correlation value here is that there's no meaningful correlations between these physiological markers on the top row here and the best time you produce during a repeated sprint test. And that's probably because the best time that you produce during a repeated sprint test is only a single trial, a single effort. It's going to be much more strongly associated with maximal sprint speed or how fast you ran 30 meters or 40 meters, because it's only a single effort. And there hasn't been enough time for things like blood lactate concentration and hydrogen ion concentration to be impacted by just one single effort. Remembering that that one single effort is of course going to be coming within the first or the second sprint during a repeated sprint protocol. However, if we account for all sprints during any repeated sprint protocol and we look at the mean value, we start seeing very meaningful correlations with these physiological markers, as we do with the decrement value. So what can we take away from this? Collectively, repeated sprint protocols or repeated sprint ability is sensitive to changes in playing level, and that actually if we're interested in linking our RSA as a proxy measurement for aerobic capacity, given that association and given the strong correlations with some of these in-depth physiological based metrics, it's not so much the best time that we're interested in, it's more going to be the mean value. And whilst we have correlations with RSA decrement as well, let's remember that in one of those previous studies we just spoke about, it wasn't a particularly reliable metric. So the final physical characteristic that we're going to focus on now is aerobic capacity. And I've kind of made these slides a blend of both the laboratory and the field. So the first thing I wanted to do was to provide a comparison of different field and laboratory based assessments that we typically use to assess aerobic capacity. And this study was conducted in soccer players, and of course we need to be mindful that our laboratory based method of assessing VO2 max on a treadmill, either through a continuous or intermittent protocol, is going to be considered our gold standard method. But I'm sure for those of you listening, you'll of course be very familiar with the various different forms of yo-yo endurance or intermittent based assessments, which serve as a relatively good field-based alternative for assessing aerobic capacity. And we're going to spend a few slides talking about why. But in this study, you can see if we look at those bottom two metrics of VO2 max and lactate, the yo-yo endurance test, which starts a little bit slower and takes longer to get going,
if you like, compared to the intermittent test, we can see that our VO2 max and lactate levels are actually quite different to both the yo-yo intermittent endurance test and our laboratory-based protocols. However, if we do compare our VO2 max and lactate for the yo-yo intermittent test to our lab protocols, we can see that those scores are actually very, very similar to our laboratory. So if we're looking to try and replicate as valid a measure as possible without being able to assess using the gold standard method, it seems like based off this data that our yo-yo intermittent endurance test is probably a better option than our initial yo-yo endurance test. I think another factor that probably gives the intermittent version of the test an advantage over the original endurance test is also that because it's intermittent, that means it probably reflects the movement patterns of the game better than a longer, slower endurance-based assessment. But also practically speaking, it will also take less time. And if it takes less time, that means that the athletes are then exposed to less distance and less load during that assessment as well. So the only question that remains really is, if it's better from a time perspective, there's less load being put through the players, and those results are better reflected against the laboratory-based methods, then why wouldn't we use that version? And we'll spend the next few slides discussing some of this in greater detail. So this is a fantastic review article, and we've got a few slides from this paper that outline some really important key considerations from the yo-yo intermittent test. So this first graph on the left here provides just a visual comparison of speed versus time for our intermittent recovery level 1 and level 2 tests. Now our darker line is for the intermittent recovery level 2 test, and you can see that essentially our first step change, if you like, happens at 13 kilometers an hour, whereas for the yo-yo intermittent recovery level 1, we start at slower speeds, and we probably end up from a volitional exhaustion perspective at the same point, but we just take longer to get there because we have a slower starting point and more step changes. If we also look at the test-retest reliability of these two tests, now we've got yo-yo test performance on the horizontal axis, but then we've got yo-yo retest performance on the vertical axis. Our black dots equate to the recovery level 2 protocol, and the white dots relate to the level 1 protocol. Now for the yo-yo intermittent recovery level 1, we had a test-retest reliability of 0.93, which is excellent, and a CV of 8.1%. So a little bit of variation and inconsistency as represented by the CV value, but also only with 28 players. For the level 2, we can see that these black dots seem to be a little bit closer towards our trend line here that's going through the data. So we have a slightly higher R value of 0.97, which is fantastic, but slightly greater inconsistency actually from between session reliability, with a CV of 10.4%, although there was a much bigger sample size of 53 players. So generally speaking, how we do in one session on the yo-yo protocols tends to be how we do on the second session as well, although we do need to be mindful of a little bit of between session inconsistency, and that may be down to a number of different factors relating to our individual players, such as acute fatigue, lifestyle management, poor sleep, tests being conducted at appropriate versus inappropriate times in the week. There's lots of different factors that can affect that, but generally speaking, it seems that test-retest reliability for both level 1 and 2 protocols is pretty good. and that if we ultimately end up at a very similar point between level 1 and level 2 protocols, why would we not choose the protocol that takes less time and in turn makes them cover less distance, which I'll go on to talk about in a minute. So this slide just provides a little bit of normative data, okay, across different sports, and you can see we've got our key here for different sports in both figures. This one on the left equates to our yo-yo intermittent level 1 protocol, and this one equates to our level 2 protocol. And if you look at your vertical axis, you can see what I mean by not only is the level 2 protocol taking less time, it is therefore covering less distance. Our vertical scale goes up to 3,000 meters, where on the level 2 protocol it only goes up to 1,400. So I think the key thing to state here is that when we compare between levels, that is to say elite versus sub-elite to moderate to recreational, we don't have data for all sports, but we do naturally see a clear decline in the amount of meters run in both protocols. So that tells you that our yo-yo tests are, again, relatively sensitive at detecting change between playing or competition levels. If we then go back to our sport-specific data and we look at our key, I think the main thing to outline here is that soccer or football clearly shows some of the best data. And while we don't have comparable sport data at all levels, it seems fair to outline that the aerobic demands represented from football are some of the highest out there in team sports. If we now look at our two protocols and we keep it specific to football, these two bar charts here are looking at the ability of our yo-yo level 1 and our yo-yo level 2 tests to discriminate against playing positions. You can see here this is goalkeepers, defenders, fullbacks, midfielders and attackers. Unsurprisingly, goalkeepers typically have the lowest performance on both yo-yo tests, and that shouldn't be a surprise given the nature of what they have to do in a game relative to outfield players. If we then consider outfield players only, we can see that the highest values typically come from the fullbacks and the midfielders, which again is probably not a huge surprise given that the fullbacks are often chasing up and down the wings to support our attackers, help get crosses in, and of course chase back for their defensive duties as and when is needed. And the midfielders, of course, often have to cover the largest amount of distance in a game because of their position. Unfortunately, we don't have data for female players on the yo-yo intermittent level 2 test, but we can see its ability to discriminate between genders on the level 1 test. If we now move to our two figures here on the right, we're looking at the association or the relationship between the level 1 test and high intensity running that happens during a game in terms of total meters. And we can see that the better performance that you do on the yo-yo level 1 test, typically the higher amount of high speed running or high intensity running you do during competitive matches, which again shouldn't be a huge surprise. If you're more aerobically fit, you can cover more distance and recover quicker in between bouts than someone who is less aerobically fit. And that's shown through an R value of 0.7, which is a pretty strong correlation with a sample size of 61. Unfortunately, we've got a much smaller sample size that's looking at the association between yo-yo level 2 test performance and peak high intensity running during a 5-minute period during a match. Now, because it's a more specific in-game metric, we've only got a 16, a much smaller sample size, but the association still, unsurprisingly, appears to be quite strong at 0.72, meaning the greater distance you cover during the yo-yo level 2 test, the greater your high intensity running during a congested 5-minute period in a match. So all in all, we've got an ability to discriminate between playing positions, between sports, between genders, and there's a pretty strong association between how well you do on these two intermittent tests and how much distance you cover during competition or during matches. So that largely concludes our discussion and our analysis around the different physical characteristics that are important for soccer and football players. So I guess it leaves me now to start offering you probably my personal opinion and suggestions on the different assessments that I would conduct if I was going to do a full physical performance assessment or testing battery with my players. Now, I will appreciate that this slide is an ideal scenario whereby probably time, budget and resources are not limited. And I understand that that's very, very rare in the real world. So I've offered an alternative to that on the next slide. But given all the information around validity, reliability, sensitivity to determine change between playing levels, positions, the effects of training interventions, and importantly, the practical viability of some of these assessments in the real world as practitioners, I've come up with what I would choose as a perhaps somewhat gold/silver standard. And when I say /silver, what I mean is I may not have chosen a gold standard laboratory test method for some of these physical characteristics, but that's because practically speaking, I don't think they're entirely viable in the real world. So if we start at the top and we look at body composition, as fantastic as the DEXA is, I think that summary slide that focused on the association between some of these skin-fold equations and their ability to showcase minimal mean bias and a strong correlation with what you would get on the DEXA means that the skin-fold method probably outweighs the time and viability of doing DEXA scans. When it comes to strength, I think that again, it's probably not practical to try and do isokinetic dynamometry, particularly with large squads of athletes, although I perhaps would use this for individual athletes coming back from specific injuries. So for that reason, when it comes to strength, I'd probably look at using both the isometric mid-thigh pull as an assessment of multi-joint maximal force production, but also look at using the Nord board so I get some kind of a targeted assessment of hamstring strength, knowing that that's incredibly important in football given the volume of injuries that happen for this muscle group, but also because because the Nordic hamstring exercise is ultimately a training tool as well as an assessment. When it comes to lower body power, I'd probably use a combination of the counter movement jump and the drop jump because I know they're assessing both slow and fast stretch shortening cycle mechanics, and I'd probably consider 1 or 2 unilateral variations of those tests. I might not use the unilateral drop jump because it's very, very advanced, excuse me, as a plyometric method. So I might run the unilateral counter movement jump alongside my bilateral counter movement jump and drop jump. And that would give us an understanding of lower body slow stretch shortening cycle ability, lower body fast stretch shortening cycle ability, and unilateral slow stretch shortening cycle ability with an understanding of asymmetry between limbs as well. Once we got to our linear and curved sprints, I think the obvious thing to do would be to take a top speed assessment and look at splits at different distances. And then there is, in comparison to linear speed, much less research on curve sprinting. But I do think that it's probably a worthwhile assessment to start including in our test batteries now, given that there's a pretty strong relationship with linear speed, velocity, and those type of movement patterns probably do occur, particularly for some playing positions in competition. Once we consider our change of direction, speed, physical characteristic, I'm very much guided by the research of Tom dos Santos. It seems that we get more 180-degree turns than we do 45-degree turns, but we also shown from some of his research that 45 and 90 degrees has perhaps had a bit more research done on it. And so I think based off his work, we know that looking at 45, 90 and 180 degree turns, they're largely looking at different motor skills during change of direction speed or change of direction performance. So I'd probably want to include all of them. And I would almost certainly do that using that Ruisi protocol that I spoke about, where we just have about 4 different 10-meter linear sprints overlapping each other to create that uniform circle, and that enables us to assess 10-meter linear sprint, but also enables us to assess dominant and non-dominant limb performance at those different angles. When it comes to repeated sprint ability, I would probably just choose something like a 6 by 40 meter sprint protocol. I might even consider 2 to 3 sets of it to determine how not just mean sprint and percentage decrement times change within a given protocol, but whether or not we start to see greater drop-offs with repeated sets. And then given the information we've just discussed on aerobic capacity, I would almost certainly choose the yo-yo intermittent recovery level 2. So that would give me my complete fitness testing battery for football. And then I know particularly from a Premier League perspective, given the EPPP protocols, I think clubs are required to run these types of testing, or the testing that they choose, at least 3 or 4 times a year. So this is, in an ideal scenario, probably the test protocol that I would run 3 to 4 times a year if I was working in football like when I was back in 2006 to 2008. However, I have to say that the practical viability of being able to do this in the real world is actually quite low, given time availability, resources, our time that we're given to analyze and act upon that data. So in reality, I would probably want to have a backup plan for a streamlined or modified testing battery if my resources and time were much less and finite. So with that in mind, I would probably look at maybe just 4 instead of 8 physical characteristics or 7 physical characteristics. I would probably keep strength in there and only focus on hamstring strength by keeping in the Nord board. I would definitely keep in my jump assessments because they serve as excellent proxy measurements for other physical performance measures like linear and change of direction speed. But I'd maybe just keep in the 2 bilateral tests because that's quick, easy and time efficient to do. And they also give me an assessment of different stretch shortening cycle characteristics. I think I'd probably just focus on linear speed, given that we know in a time constrained environment, given that we know that the relationship between linear speed and curvilinear speed is quite strong. So in this instance, I don't think we lose anything by keeping the same linear sprint protocol. That is to say, the same max speed test, but with splits. And then if I had to choose just one change of direction speed assessment instead of my 45, 90 and 180 degrees, I'd probably choose the 505 change of direction speed test. One, because I'm confident in its usability and reliability, given the volume of research that's been conducted on it. But two, because based off Tom's research, we know that 180-degree turns are some of the most common angles that soccer players are required to change direction during training and competition. So if I was short on time and resources, this is probably my modified testing battery that I would undertake as a practitioner in the real world. So I hope you've all enjoyed this information on physical performance assessments, discussing various different field and laboratory based protocols for football players. I'd like to give a very big thank you to all of you if you managed to get to the end of this presentation. A big thank you to the Strength and Conditioning Society as well for inviting me to contribute to what is no doubt going to be just a phenomenal resource for practitioners working in the sport. And if anyone would like to get in touch about any of the information presented here or anything else, my email address is there, and I'm more than happy for anyone to contact me should they wish. Thank you very much.